Okay, we'll have the Right. Okay. Thank you. I'd like to welcome you all once again for another webinar. And our speaker for the day is Dr. Dimitra Atri. I'd like to welcome you. Our speaker for the day is Dr. Dimitra Atri. He is leading the research program on Mars at the Center for Space Science in New York University, Abu Dhabi. And his expertise are in astroparticle physics, planetary science, and astrobiology. This short introduction, I'll pass it on to our speaker today. So over to you, Dr. Dimitra.
Okay, thanks, Bala, for the introduction and for inviting me to this excellent webinar. Yeah, it has had some really interesting talks, and I hope you're able to listen to me clearly and see my screen.
Yes.
So, okay, great, excellent. Yeah. So I'm based at NYU Abu Dhabi. New York University now has 3 campuses in addition to New York City. It is now based in Abu Dhabi and in Shanghai. And at NYU, we have a very extensive research-based program for both undergraduates and graduate students. So there are a lot of people doing space sciences broadly. Recently, one of the most exciting things has been the Hope Mars mission. Some of you might have heard about it. Last month, this was the first interplanetary mission by the UAE. And just yesterday, as I was in traffic, I saw there was a bus and there was an ad going on that Hope Mars mission has completed 100 million kilometers. So the general public is also very excited about this mission. The country UAE is very young. It has a very new space program. So a mission like this is a very huge deal. In addition to this, last year, the UAE also started a human spaceflight program. So here on you see astronaut Haza. He went to the International Space Station. There will be 2 new astronauts going to the space station sometime early next year. And the UAE Space Agency is planning to do experiments on board the International Space Station. So we are closely collaborating with them, and we have a research program on Mars. We are studying how solar radiation interacts with the Martian atmosphere, and we'll be analyzing data from the HOPE mission. Plus, we are developing capabilities to do experiments on board the International Space Station. And we are establishing a lab here to do microgravity and radiation experiments here in our labs. And there are many students. So here you see the names of a dozen students who are already working with us. There are many students who have recently joined, and so it is an ever increasing program. Although due to COVID, there are some funding restrictions, but we are hoping that they will be cleared soon. So one important thing, because I was discussing this with Bala early on, that we also have a space science webinar series. And in fact, right after this webinar, I have to go and prepare for that one. And basically, it has people from around the world talking about how space weather interacts with planets, especially terrestrial planets. Mars is a big thing now because 3 new missions have gone. And so we are really interested in how space weather interacts with Mars. And so you are more than welcome to participate. Just go to the Center for Space Science website and you'll get a Zoom link. And through that, you can do that. It is at 4:30 p.m. Indian Standard Time, and we host this in collaboration with the UAE Space Agency. So the topic of today's talk is related to habitable planets. And when we were growing up, we only knew about 9 planets. We lost one, but we found many more. And it is truly mind-blowing that we know so much about planets beyond the solar system now. So there are about 4,000 exoplanets known so far. The number is growing exponentially every year. From our solar system, we knew that there are 2 types of planets, terrestrial planets, so Mercury, Venus, Earth, Mars, and gas giants like Jupiter and so on. But these discoveries of new exoplanets have shown a new category, which is called super Earth or sub-Neptunes. The name is still controversial. It is not clear what we should call them, but there is a category of in-between planets. Now the question is, we know so much about exoplanets. How many of them are habitable? And so for me and for this audience, I think this is one of the biggest questions, which ones are habitable planets? And so let us understand habitability. So you must have seen this slide. This is mandatory in any astrobiology talk. And so planetary habitability is described as a zone around a star where the planet is able to sustain liquid water on its surface, and you see this habitable zone. You see on low mass dim planets, the habitable zone is much closer to the star. And for giant bright planets, the habitable zone is much further. And you can see that Mars and Venus are slightly outside the habitable zone. Earth is right in the center because we have defined the habitable zone that way. So basically, habitable zone is a place where you can find planet with oceans in it. So it is a very geocentric approach towards habitability. And I will discuss more about this concept later on in my talk. Now, this definition is a great place to get started about habitability, but it ignores, it assumes a constant stellar flux. And we know that this is not true. Even our sun has evolved over the last 4.5 billion years. Even on timescales of a decade or a century, there are fluctuations. There are events such as coronal mass ejections, flares, and so on. And they disrupt conditions around the planet. And so those are also extremely important from the point of view of habitability, both on short and long timescales. And so all these activities, all these stellar activities are broadly referred to as space weather. So on the sun, as I was saying, there are coronal mass ejections. So you have these huge blobs of plasma ejected from the sun. There are solar flares. You have very high energy photons, very high flux of these photons. You also have accelerated charged particles called solar proton events directed towards the Earth. Very, very high energy protons, GeV, 10 GeV protons directed towards the Earth. And all of them interact with the geomagnetic field, with the atmosphere. You can see auroras. But the flux itself is not that great on the surface of the Earth, and that's why we don't have any noticeable effect on the Earth's surface or on biology, because we are protected by a thick shield of our magnetic field, plus atmospheric column density is high on Earth, which might not be the case on exoplanets. So the focus of my talk today is how does space weather impact the habitability of planets? And it is extending the definition of the habitable zone. So in addition to the thermal radiation I discussed, there is many non-thermal processes that eject radiation. So this is the basic electromagnetic spectrum. You see visible light, but sun also emits in X-rays, gamma rays, and UV. And they also interact with the planetary atmospheres in a variety of ways. In addition to the in addition to the electromagnetic spectrum, you also have charged particles, which I'll talk about later. And I call this broadly as the dark side of habitability, that these are all the processes that destroy a planet's atmosphere and reduce the chances of habitability. And so the concept of habitability is ever evolving. So as I mentioned earlier, we have solar proton events. These are high energy protons ejected from the sun during flares. And you can measure using neutron detectors and other instruments using GOES spacecraft. You can measure the energy spectrum of these events. And so these are three events. These are the 1956, 72, and 1989. These were three major solar events recorded in recent history. And the spectrum of charged particles was determined by stitching together data from a number of experiments. And so based on how these large events eject solar protons, we can then extrapolate this and we can understand how such events might impact extrasolar planets and other planets within our solar system. In addition to this, we also live in a galaxy, so we have radiation not just from the nearby star, but from other galactic sources. So for example, nearby supernovae. We already have a background flux of galactic cosmic rays, which is well known. And so a planet is also impacted by those. This is the charged particle spectrum compiled by Karlsruhe Institute of Technology. You see a number of experiments. And the flux is on the vertical axis, the energy is on the horizontal axis. So let me explain what the energy scale is. So visible light is between 2 and 3 electron volts. The energies you see here are in GeV, so billions of electron volts. So charged particles from the sun are usually in keV or MeV scale, so 1,000 to 1,000,000 times more energetic than these photons. In galactic cosmic rays, particles are in GeV and above, so you have a billion times or 10 billion times more energetic than these photons. So even though their flux is low, their energy is extremely high. And so they can interact with planets in different ways and have different types of effects, which I will discuss now. So what are the different impacts of this radiation? So flares, stellar wind, galactic cosmic rays. One is atmospheric escape. So when you have radiation interacting with the planetary atmosphere, it heats the planet. And when you heat a gas, it expands, and so it can expand into space, so that's why you have erosion of the atmosphere. There are many other mechanisms through which the gas, the individual component of the atmosphere, gains energy by interaction with radiation and it escapes. And we see this very well in case of Mars, that how solar activity increases the erosion rate of the Martian atmosphere. And so from this, we can extrapolate how stellar activity can impact planetary atmospheres in general. We also have these photons and protons causing chemical changes in the atmosphere of the planet. So for example, on Earth, it can break the bond of nitrogen and oxygen, and different NOx compounds are formed, and they start a series of chemical reactions which have very important implications. For example, ozone depletion, as you all know, is very tightly linked to solar activity. In case of gas giants, you have all these processes and they can be observed because gas giants are large, and a lot of telescope time is allocated to the study of gas giants, so many of these processes can be observed on gas giants. In addition to having the impact on the atmosphere of planets, this radiation is so powerful, it is so energetic, that charged particles can propagate down to the surface of the planet, and they can increase the radiation dose on the surface of planets. So how does this direct radiation exposure have an implication on the habitability of these terrestrial planets? And if you're close to the galactic center, you have other high energy astrophysical sources which can impact the habitability. Now, I was talking about all these negative things that you have radiation which can change the chemistry of the planet, it can erode the atmosphere of the planet. But it is a double-edged sword. It can also have positive effects. So for example, when planets were just formed, the idea is that they were formed with the giant envelopes of hydrogen and some helium. And because of this atmospheric escape, that atmosphere was completely eroded, and these secondary atmospheres like nitrogen or CO2 atmospheres that you see now, these were formed more complex. And so these are very important for terrestrial life as we know it. Direct radiation exposure can also lead to organic synthesis, as it can be seen in interstellar ices, in situ data from the comet. Plus, in lab experiments, it can synthesize prebiotic compounds very useful for life. And finally, it can induce chemical disequilibrium, which is useful for metabolic activity. Whether or not it can be useful in case of Mars, I'll be discussing it later on. So how do these charged particles interact with the planetary atmosphere? Well, their energy is extremely high. So like the collision experiments you see in CERN, you have a shower of secondary particles. These are highly unstable charged and neutral particles, and they form a shower of secondary particles. These secondary particles then again interact with other particles in the atmosphere. And so you have this shower going down to the surface. And these are all the processes which might not be that interesting to this audience, but just for the sake of comprehension, I have given them here. Some of these particles are highly unstable. They decay very quickly and form other particles. So on the ground level, you have a very high flux of electrons and muons. Muons are basically heavy electrons. They are basically 200 times heavier than electrons, and they can propagate several meters below the surface of planets. In Earth, it happens all the time. So I use this astroparticle physics tool called CORSIKA, and I apply these to different types of planets and in the solar system and beyond. You can see how different types of components interact with atmosphere in different ways. So this is from the Earth's atmosphere. This is how a gamma ray, a proton shower, and ion shower interact. Blue are hadrons, red is the electromagnetic component, so electrons and photons. Okay. So now, once we know how to model the interaction of radiation with the different types of planets, we can then do calculations of atmospheric chemistry and atmospheric escape. And so this is a model developed at NASA Goddard Space Flight Center. And we use all this data that we get from simulations in this model, and we calculate atmospheric chemistry changes. So from the Earth, we can take, let us say, radiation from a flare, and we can model the atmospheric chemistry changes observed on the Earth, and then we can compare it with the data. And as I was telling earlier, you have different NOx compounds, and ozone is depleted. Ozone is converted to oxygen. And so if you can apply this to other planets, then you might see, additional oxygen production. And that might not necessarily be a biosignature, but you can see that using this mechanism. And ozone depletion on Earth, as we know, it is very harmful to biology on Earth because it directly interacts with the DNA. The UVB band is extremely harmful. Then, in terms of atmospheric escape, it's a very complex problem, and we recently submitted a paper where we take the extreme ultraviolet component of this radiation, which is called XUV, and we calculated how much heat will be deposited in different planets. And we looked at the long-term implications of this XUV radiation coming from the star, both in terms of the steady state radiation plus the radiation which is emitted in form of flares. And we compared different scenarios of planets in the habitable zone, whether it is going to increase the chances of habitability or decrease the chances of habitability. So we have done this extensive analysis, and it should be out soon, and I'll be happy to share with you guys. As I was mentioning earlier, that we test all these models with Mars. So atmospheric escape is a very, very important subject on Mars. There are different types of mechanisms. So in this cartoon, you see different channels of escape, and we are modeling some of these. We have collaborators from different institutions who are helping us with this. We are using all these tools that I was talking about, and we are already using data from NASA's MAVEN mission to validate our models to see what kind of response we get both from models and from the data. And we are hoping that with the Emirates Mars mission going to orbit next year, we will start getting this data. And we then apply all these models to extrasolar planets to figure out how it impacts habitability. Okay, so far I have talked about all the indirect effects. So how does this radiation impacts the atmosphere of planets? And once the atmosphere is impacted, atmosphere governs the habitability of planets. But what about direct effects? How does radiation directly affect biology? And so in order to do that, let me introduce a quantity. It is very well known. It is called the radiation dose, and it is measured as the energy deposited in a substance per unit mass. Gray was the unit popular several years ago, but now everything is measured in sieverts. It takes into account how different types of radiation interacts with matter in different ways. So for example, photons will interact with any substance in different way than a proton, for example. And so in this table, you see this radiation quality factor, and it tells you basically that neutrons in 100 keV to 2 MeV range are 20 times more dangerous than, let us say, electrons or photons. And neutrons are a big problem for astronauts, for example. So once we know how to calculate the radiation dose, we then use our models to calculate radiation dose on the surface of Mars. So this is the Curiosity rover called the Mars Science Lab, or MSL. And it has an instrument as shown here called the Radiation Assessment Detector. So it basically measures radiation dose on the surface of Mars. So we can measure the background flux of galactic cosmic rays. In case of a solar event, you see radiation enhancement both on Earth and on Mars. So there was a major event in 2017, and we could clearly see the enhancements right at the Sun, on Earth, and on Mars simultaneously. So it was great. And so this instrument, as I said, is great for calibration. Mars has a very thin atmosphere. Its column density is 22 grams per centimeter square compared to the Earth, 1036 grams per centimeter square. We use this code called GIANT4. It is a code developed at CERN to simulate the interaction of charged particles, and we have modified it to work with Planet. We also take data from the Mars Climate Database because we want to have a realistic atmosphere of Mars. And then we simulate the impact of galactic cosmic rays and solar proton events. Now, in addition to this, we are also interested in human spaceflight. All space agencies are now very seriously thinking about human long-term space missions, especially missions to Mars, and how does this radiation interacts with the human body. And so we are using this GR4 tool to calculate how much radiation is deposited in each organ. And we can compare our simulation results with actual medical data. So radiation therapy, as you all know, is where a patient's malignant part is exposed to radiation. And so we can compare those two data sets directly and figure out the health effects of radiation exposure in case of astronauts. And many students are working on different aspects of this too. And we have a paper which will go out recently, which will calculate all these things, the background flux of galactic cosmic rays, how it changes the radiation dose on the surface of Mars, and long-term implications of human missions to Mars. Now, moving on to exoplanets, this is Proxima b, as you all know, the closest known exoplanet. On the left-hand side, you see it is shown the Mercury's orbit, the closest planet to the sun. On the right-hand side, you see the green zone. It is the habitable zone of Proxima b. So this illustrates that how close Proxima b is to the planet. Now, having such a close habitable zone, such a short habitable zone, it means that those planets are also highly susceptible to any kind of stellar activity. And we know just by observing the sun and nearby stars, then you can have extremely energetic flares. And for the planets which are in the habitable zone of such dim stars, these are going to have a huge impact on the planet. So it can drastically increase the atmospheric erosion. It can have significant impact on the chemistry of the planet. Plus, it can greatly enhance the radiation dose on the surface of the planet. So even though you might have life on the surface, it might get destroyed on multiple occasions because these flaring activities, it is very frequent if you look at large time scales. And stars, when they are young, they flare at an extremely high rate. So this is one of the main concerns with these low mass stars such as M dwarfs. 70% of stars in our galaxy are M dwarfs, and their habitable zones are extremely close. So this space weather induced effects are extremely important when considering their habitability. Okay, so now using all this solar data, terrestrial data, Mars data on exoplanets is extremely difficult because here we can measure things, but in case of extrasolar planets, the measurements are not that great because we don't know a lot of things. Plus, we cannot resolve the atmospheres of these planets in great detail. So as you can see, there's a big difference between what you expect and what the actual reality is. And we are hoping that with more missions and more data, things will become clear. And so here I list all the different factors which needs to be improved in order to correctly apply our work on terrestrial planets in the solar system to extrasolar planets. So for example, we have measured all the different XUV photon spectra, particle spectra from the sun. But these measurements are extremely difficult from super flares on other stars. So for example, you can't detect protons coming from other stars. Another thing is that although we see these photons going at very, very high energies from other stars, we don't know how many protons are ejected from these because we can't observe protons from other stars. So we have to extrapolate based on the sun. We don't observe these planetary atmospheres in great detail. That is a big uncertainty. We have very little information about the magnetospheric activity of that planet, and we don't know how the particles will propagate through the interplanetary media in that particular stellar system. So despite all these, based on the best data that we have, how can we extrapolate that to understand the habitability of extrasolar planets? And so first of all, we take a numerical model and we take different types of magnetic field scenarios. So at the very top, you see a magnetic field on a terrestrial planet, which is just 5% that of the Earth, very weak magnetic field. And right at the very bottom, you see a planet with 10 times higher magnetic field strength than the Earth. And basically on the plot, you see a filter function which tells you the efficiency at which different types of charged particles at different energies, how likely they are to penetrate the atmosphere of that planet. And based on that, we can do a number of calculations. And we have done that. And I will not go into more details on how we did these simulations, but I'll discuss the basic results. So one question that I was interested in is, you have two types of shielding. One is the atmosphere itself. The other one is the magnetic shielding. So which one is more important? And so we found that atmospheric depth is a major factor in determining radiation dose on the planetary surface. The radiation dose is reduced by 3 orders of magnitude if you increase the atmospheric depth by an order of magnitude. So that is one big factor. The planetary magnetic field is important, but it's a less significant factor compared to atmospheric depth. So if you increase the magnetospheric strength by an order of magnitude, the dose is reduced by a factor of 30. So not that much as in case of the atmosphere, but it does get reduced. And so in order to find a habitable planet, the most important factor in my opinion would be, based on this data, a planet with some magnetic field but with a significant atmosphere. Now, when I was talking about this radiation dose in terms of sieverts, we can calculate radiation dose using different types of flares, using this filter function, and calculate radiation dose on the surface. But what does this radiation dose tell us? So let me give you some numbers. So a dose of 50 millisieverts and above is considered harmful to humans. Between 1 and 5 sieverts causes sickness and death for humans. So NASA has set 1 sievert as the career limit for astronauts. So if they are exposed above 1 sievert, they are grounded, they can't fly into space anymore. A dose between 6 and 10 sieverts is lethal for mammals. All insects die for a dose up to 1,000 sieverts, and the most radio-resistant organism that we know is an extremophile called Deinococcus radiodurans, which can survive up to 100,000 sieverts of radiation dose. And so as you can see that as you increase the radiation dose, the probability of an organism surviving becomes extremely low. And this is also a kind of a filter function. So if I calculate the planet has 1,000 sievert of dose from a given flare, then you can assume that most complex organisms, if it is terrestrial type life, will get destroyed in that event, and only extremophiles can survive. Here, this is one of my recent papers where I have taken the energy spectrum of different events. Now, these events are of different types. So some events are called soft events, where you have low energy particles, and low energy particles produce a lower dose. There are some events called hard events, and these produce highly energetic particles, and highly energetic particles produce higher radiation dose on the surface. And on this plot, you see the radiation dose distribution in 3 scenarios. 3 types of flares. So 10 to the 11, the green one is a large flare which is seen in major flares on the sun. 10 to the 13, which is blue, and 10 to the 15, red. They have not been observed on the sun because they occur on much longer time scales. But they have been observed on other stars based on observations from Kepler, TESS, Gaia, and so on. And so we take what we understand from solar data and extrapolate to these stars. And as you can see, in extreme cases, radiation dose for hard events can go up to 10 to the 3, 10 to the 4 sieverts, which means that if there is, mammals and life like complex life on the planet, the probability of its survival would be extremely low. And so this is one case. It is in case of Proxima b. It is very close to the host star. There are many, many stars, planets close to the host star. So this is another way of representing that data. And so here I have shown how much is the radiation dose enhancement on an exoplanet compared to the background radiation level on that planet. So on the left, you see number of exoplanets, TRAPPIST system, Proxima b, Kepler 1229b, and so on. On the top, you see 30, 100, 300, and so on. And these are different atmospheric depths that you see. So 22 grams is the Martian atmosphere. And so this 30 is close to that. And 1000 is close to the Earth's atmospheric depth. And so you see in each of these cases, we can calculate the background flux of cosmic rays based on, because the flux of particles is very well known in the galaxy. And once we know the different magnetic field configurations, we can calculate the background flux of galactic cosmic rays. And so with one event, you can see in some cases you have 4 orders of magnitude increase in radiation dose on the surface of those planets. And it is extremely high. And so this is another demonstration on why stellar activity is extremely important when considering habitability of extrasolar planets. Now, as I mentioned earlier, that certain extremophiles can survive in these extreme environments. And these extreme environments are defined by humans, right? Most objects that you see in nature are extreme by our standards. So the question is, if we study planetary, we study habitability from the point of view of extremophiles, can we find habitats in the solar system? And how would it impact our concept of planetary habitability? And based on that, can we calculate the survivability and possible detection of such extremophiles in the solar system? And so this is the new line of work that I am interested in. So I take this example, very interesting example. About a decade ago, there was a discovery in a gold mine in South Africa. It is 2.8 kilometers deep. It is surrounded by radioactive substances, so it is radioactive. And 2.8 kilometers deep, there are no photons, almost no water. There is a bacterium, an extremophile that survives there. It is called Desulforudis audaxviator, or I like to call it the gold mine bug. Not only it is surviving there, it is actually extracting energy from radioactivity. And that I found this very, very interesting, that organisms can extract energy in such radioactive environment. So how does it do that? Well, basically you have pyrites, like it is very common in the solar system. It is here on the Earth. There are traces of water there. So all these radioactive substances, they are ionizing the medium. They're breaking these different bonds. Different radicals are formed, and it is using those byproducts for its metabolism. So the mechanism here is called sulfate reduction. It is using these sulfates to power its metabolism. Hydrogen is also very useful for microbial life on Earth. It produces hydrogen. So my question was, okay, if on Earth we have this extreme environment by our standards where an organism is able to extract energy using this mechanism, using radioactive substances, how about in case of Mars? Mars has high radiation levels. Can such an organism survive on Mars? And so I proposed a hypothesis, and the hypothesis goes this way, that photons, so for example, normal photons, ultraviolet, they cannot penetrate below the Martian surface. And on the surface, the radiation dose is extremely high for any type of complex biology to survive. And that is why we haven't seen anything on the surface of Mars so far. But this radiation, this galactic cosmic rays, these protons are so powerful that they can penetrate several meters below the surface of the planet. Okay? And so when they penetrate below the surface, they are going to induce several chemical changes. And instead of having these radioactive substances causing these chemical changes, you can have galactic cosmic rays, secondary particles causing these changes. And so I have coined this galactic cosmic ray induced radiolytic zone. And this is the zone where it is up to 3 meters deep, where this radiation can induce significant amount of chemistry below the surface of Mars. I have used this same numerical code which I use for Mars and extrasolar planets to calculate energy deposition below the surface. And our model, as you know, is well calibrated to work with Mars. So this, on the vertical axis, you have the energy deposition rate in electrons per grams per second. And on the horizontal axis, you have depth below the surface of Mars. And this green band, this is the zone. This is the number between around 10 to the 6 electron volts per grams per second. This is the exact amount of energy available to this organism right here. And so if you have a similar chemical environment there with the same amount of energy availability, can an organism, if life were to exist on Mars several billion years ago, can certain extremophiles still survive using this kind of mechanism? And so I've recently published this paper in Scientific Reports, and it is about investigating the biological potential of galactic cosmic ray-driven radiation-induced chemical disequilibrium in the Martian subsurface environment. So very complex title, but basically the idea is this radiation penetrates below the surface of Mars. It induces this chemical disequilibrium, which is extremely useful for any kind of life. And the question is whether this kind of disequilibrium can be used for metabolic activity. And so it is a source of chemical disequilibrium. There will be tons of electrons produced below the surface. Electrons are crucial for any kind of metabolic activity. There is production of hydrogen, which is useful for many microbes. It produces sulfates, as it is used by the goldmine bug. And so the question is, does such a life exist below the surface of Mars? And so to test this hypothesis, the ExoMars rover, which was originally planned to be launched in 2020, and just like all our plans are getting cancelled, this mission got postponed, and now it will be launched in 2022. It is a mission by the European Space Agency and Russia's Roscosmos. It is a rover with the capability of penetrating 2 meters below the surface of Mars and looking at the chemical environment and signs of life. And so it will test this hypothesis whether organisms can survive in such environments. Now, overall, the take-home message is that stellar activity and this high energy radiation can impact habitability in two ways. One is by interacting with the atmosphere of different types of planets, by changing its chemistry, by atmospheric erosion. It can also directly impact life on the surface. It can change the chemical environment below the surface of planets in case the atmosphere is very thin, like in case of Mars. But just like in any astrobiology research that you see, that it is always incomplete, because I am an astrophysicist and there is so much that biologists or geochemists or other disciplines, they can contribute to it. And so I look forward to collaborations, people who attend this webinar, if they find this work interesting and if they can align somehow to any of these studies, then they are more welcome to collaborate with us. We have a growing group of students who are working on different aspects of this research. Studies of Martian atmosphere, in studies of astrobiology. And so if you are interested, just drop me an email. You can get in touch with me through Twitter. And we have a webinar series every Tuesday. So right after I'm done with this, I will start preparing for that, and hopefully I'll see some of you there. So with that, thanks a lot for listening, and thanks Bala for inviting me for this opportunity. Thanks a lot. Sure. Yeah, sure. Yeah, can you elaborate on chemical disequilibrium in context of metabolic activity? Yeah, so let us take, for example, any system. If it is in equilibrium, then you have the same products. But if a system is in disequilibrium, then it is going to produce new chemical products, and that is what we need for life. So for example, let us take the case of photosynthesis. You have substances on Earth which are not useful for life, but because of energy from photons, there is a complex process through which electrons are generated, and those electrons are then used for creating ATP, for example, used for all life. And so this chemical disequilibrium, this is how it is important for metabolic activity. Second question is, what about habitability and habitable zone around variable stars? The same thing. I think this question is really important, because in case of variable stars, you already have a large variations in flux, and so it will have a big variation on the different types of effects I talked about. It all depends on the magnitude of change of the overall flux, plus the energy of radiation coming out. So for example, if you have just the thermal or XUV type radiation, it will interact with the upper atmosphere of the planet. In case of high energy radiation, it will impact the lower atmosphere and even the surface radiation dose. Can you tell anything about research on D radiodurans? Yeah, so all astrobiologists who study with radiation, radiodurance is their favorite extremophile. And so you'll find tons of research papers on this. And its key to survival is that because that this extremophile lived in extremely dry environments, it has developed capabilities to repair its damage in a highly efficient way using least amount of resources. So it does get damaged by radiation, but its repair mechanism is unprecedented. And so that is the key. It's a miracle. Yeah, not seen in any other type of organism on Earth. How much amount of CO2 escaped from Mars per year due to solar and different energetic radiation? Well, the exact numbers can be found in the papers. It depends once again on the flux of radiation and the energy of that radiation. And so solar wind, for example, if it is strong, then it can enhance the escape rates up to an order of magnitude as it can be seen with recent MAVEN data. In case of solar flares, if the flare is several magnitudes of higher than the typical flare that you see now, it can enhance the escape rate by several orders of magnitude. So it's very tightly related to the flux of the radiation being considered. Another question was, what about the habitability on tidally locked planets? Yeah, so all the planets that I was talking about, these M dwarf planets, because they are very close to the host star, they are thought to be tidally locked. The thing with tidally locked planets, all the simulations have suggested that if they have a significant atmosphere, then they will be able to redistribute heat through winds. And so the atmosphere becomes in equilibrium, even though one side is always exposed to the star. And yeah, so that's there. Yeah, what are the effects of radiation on Venus with respect to Mars's atmosphere? Okay, so Venus, although it is much closer to the sun, it has a very thick atmosphere. So it has 90 bars of atmosphere, 90 times higher approximately than what we see on the Earth. Mars has a very thin, less than 2% that of the Earth. So Venus, it does have atmospheric erosion, it does have atmospheric escape, but it also generates atmosphere through geological processes, and that's why we don't see that big of an effect on Venus than we see on Mars. Next question is, in extreme magnetic field conditions, how that habitability condition changes. Yeah, so if you have very high magnetic fields, as I mentioned earlier, you will have less flux of charged particles and less chances of disruption of the atmosphere. And so it will lead to more favorable, it will be more stable, the environment would lead to more favorable conditions to life. Although in case of a planet, let us say you have a protoplanet with very high magnetic field and it has a rich, large extended hydrogen envelope. Now, because of the magnetic shield, the amount of reduction in the atmosphere of that planet will be less. So it is less likely to form a secondary atmosphere. So that is also a disadvantage. So it's a complex question and it depends on case to case. Next question is, can you create a SPE effect in lab and study the effects on organisms? Yes, it can be done, but it is very expensive. So for example, these proton beams, they are generally reserved for particle physics experiments. And so to get a time in the beam to expose these organisms is extremely difficult. Some people have done this, but the thing is, the radiation that you see on the surface level is mostly made of electrons and muons. And so there are some experiments that have been done, but more experiments need to be done, and we are building capabilities here so that we can directly test these things here in the lab. How does oscillation of magnetic field affect atmospheric erosion? So very good question. So magnetic field controls the flux of charged particles on the planet. And so as the magnetic field weakens, you have enhanced flux of protons, which means enhanced rate of atmospheric erosion. There are other channels of escape. So for example, solar wind, when it interacts with Mars, solar wind also has a magnetic field in it. So it carries away these particles with it. So that is also an escape mechanism. And with higher magnetic field, that rate is certainly going to be reduced. Cosmic events can somehow be related to resistance of bacteria. Yeah, so we don't know this yet because radiation resistant organisms, how did they evolve? How did they get such radiation resistance? This is an unknown. And one hypothesis is that maybe back in the past there was an increased rate of these energetic events. Maybe the radiation dose was extremely high, and so these organisms learn to survive in these mechanisms. But this is still an unanswered question. Yeah, great question. Mm-hmm. No. So the magnetic field changes, as you know, our magnetic field changes polarity, but the effect is a very minimal. So, for example, radiation dose on the surface versus radiation dose, let us say, on a mountain 14,000 feet higher, there's a significant difference in height. There is a difference in radiation dose, but very minimal impact on life. So Earth's magnetic field, even if it changes polarity, the effect is going to be very minimal on life. Yeah. Yeah, thanks a lot. Thank you, everyone. I hope I was able to communicate my ideas, and please feel free to get in touch with me by email. You can follow me on Twitter, and let us look forward to more exciting science. Thanks, everyone. Stay safe.